Hello everybody and welcome to our discussion of light. Today we're going to talk about light as a wave because it turns out we can approach looking at light in two different ways. One as a wave and one as a particle or a ray. Today we're going to talk about the wave nature of light. So to examine light as a wave we need to know what type of wave this is. And light is an electromagnetic wave. And hopefully you all remember that electromagnetic means it does not need a medium to travel through. And on top of being electromagnetic, it is transverse. And this is important because of the way that light interacts with itself and with other objects. So light is a transverse electromagnetic wave. And it turns out that light has a very specific speed when it is traveling through a vacuum. We call this the cosmic speed limit, and it is 3 × 10⁸ meters per second. Really, really, really fast. So in a vacuum, this electromagnetic transverse wave travels at 3 × 10⁸ meters per second, which is 300 million meters per second. So remember, velocity can be equal to the frequency of a wave times its wavelength. And this number is going to be constant for us. And if that number is constant for us in a vacuum, that means the frequency and the wavelength need to change together in tandem. So what do I mean by that? Well, what I mean is if the frequency of this wave increases, the wavelength has to decrease by the same amount in order for the velocity to stay the same. So let's talk about different frequencies of light for a second. When I say the word light, you probably usually think of the light from the lights in your room or the computer screen or the sun. But it turns out light is much more complicated than that. Light is what cooks your dinner in a microwave, and it's what you listen to on the radio, and it is what gives you a sunburn in the middle of the summer. All of those are electromagnetic waves, and they are part of the same spectrum as the visible light that we see. So this is the electromagnetic spectrum, and it tells us what different kinds of waves we have. At the low energy end of the spectrum, which is where frequency is really low, so this is frequency, low on this side and high on this side. And remember, if the frequency is low, that means the wavelength has to be big in order for the speed to stay the same. So over on the left side of the spectrum, the frequency is low, so the wavelength is very long. And at the right end, the frequency is high, so the wavelength is really short. And what this translates to, that is really important, is that the energy of a wave is related to the frequency and the wavelength. The lower frequency you have, the lower energy you have. So when we start with the low frequency end, which is the low energy end, we have radio waves. Radio waves are exactly what they sound like. It's what you pick up with your radio antenna in your car when you're driving along. Those are electromagnetic transverse waves. It just happens that they have such a low frequency that our eyes can't see them. So we use them for something else. We use them as radio signals. Now, the next step up from radio waves is microwaves. And microwaves is where the energy starts to get large enough that these waves actually interact with things. And microwaves interact with water. Microwaves have a very specific frequency such that they interact with water molecules and make them vibrate. And as they vibrate faster and faster, they heat up. That's exactly how a microwave works. A microwave sends these electromagnetic waves into your food and vibrates the water molecules until they get really hot. And then your food gets hot. The next step up from microwaves is what we call infrared. You may have heard of this before. Infrared is basically heat. So, you've probably all heard of night vision goggles and maybe even seen some on TV and things. The way that night vision goggles work is instead of picking up visible light, they pick up infrared. So, this electromagnetic wave has enough energy that we can sense it. We can actually feel infrared waves. That's what you're feeling when you put your hand next to a really hot car on a summer day. You are feeling those infrared waves, but we can't see them. The only part of this spectrum that we can see is the visible light part, which is a really, really tiny part of this spectrum. So the electromagnetic waves that our eyes can pick up are part of what we call the visible spectrum of light. Beyond the visible spectrum, we get things like ultraviolet, which is beyond what we can see, but that's when these high energy, high frequency waves start interacting with things like our cells, and that's where sunburns come from, is from ultraviolet light. These waves have so much energy in them that they can actually cause damage to your skin cells. Beyond ultraviolet are X-rays, and beyond that are gamma rays and cosmic rays. Now, gamma rays and cosmic rays have very, very high frequencies, so they have super high energy. These are the kinds of things that can cause mutations in your DNA. So these electromagnetic waves with energy this high can actually penetrate your skin, get into the nucleus of your cells, and break up your DNA. And when it breaks it up, it will reform with kinks in it or some kind of misalignment. And when that happens, it will replicate as a cell, and then that bad DNA gets made over and over and over again. So gamma rays and some X-rays have been known to cause cancer because that's exactly what they do. They mess with the DNA in your cells because they have such high energy. Now, the part that we're interested in is the visible spectrum. So the visible spectrum goes from a low frequency, which is red, to a high frequency, which is blue. The low frequency of light is about 4 times 10 to the 14 hertz, which is a lot. That's still really high. And the high frequency of light is about 7.5 times 10 to the 14 hertz. Now, we normally don't talk about visible light in terms of frequency. We usually talk about it in terms of wavelength. So the low end of the wavelengths that we can see are 400 nanometers. Oh, I'm sorry, that's the high end. And the low end of wavelengths that we can see is 750 nanometers. So 750 nanometers is red light, and 400 nanometers is blue-violet light. The shorter the wavelength, the higher the frequency. So we can see the entire spectrum of the rainbow. We can see from 750 nanometers all the way up to 400. And it turns out some people can see a little bit more on either side depending on how sensitive their eyes are. But when we talk about light, we have primary colors that are made. And you've heard of the primary colors in art, right? You have to mix things together to get other colors. And that's exactly what light does, but light's a little different than pigments. The 3 primary colors of light are red and blue and green. Green is a primary color of light. We get secondary or additive colors of light when we mix these together. And some of them are intuitive and some of them aren't. So when we mix red and blue, we get magenta, which is like a purpley color. It's something you would totally expect to get. When we mix blue and green, we get what we call cyan, which is a bluish green color. And that totally makes sense. The one that is probably going to totally blow your mind is when you mix red light with green light, you get yellow. So in the pigment world, yellow is a primary color. you mix it with other things to get more colors, like you mix yellow with blue to get green. But with light, yellow is a secondary color. We get it from mixing green and red together. So to make a little visual here, we have green and blue on the bottom mixing to make cyan. And we have blue and red on the left side to make magenta. And we have red and yellow on the right side, or red and green to make yellow on the right side. And when you mix all three of these colors together, you get white. So it turns out the white light that you see when you walk into a room is a mixture of red, green, and blue light. It's all of the colors of the rainbow mixed together. Now, these are different from pigments, right? Babs would tell us that the three primary colors are red, blue, and yellow. And when you mix all of them together, you get black. And that's because pigments are what we call subtractive. So when light reflects on an object, the color of the object is the light that we see reflected. So if I'm wearing a red shirt and I walk into a room and the lights are putting off white light, that white light is a mixture of all of the colors of the rainbow. And my red shirt is going to absorb all of those colors except red. So my red shirt will absorb the violet, green, blue, yellow, and orange from that white light. And it will reflect red. So this is the only color that comes off the shirt and to our eyes. And that's why it looks red. It's the same thing with pigments. If you have red paint, that red paint is absorbing every color of the rainbow except red. And that's why we see it as red. So when you mix red and yellow paint together, you have a red light being reflected and a yellow light being reflected. And when you mix those together, you get orange. If you have blue and yellow paint, you have a blue light being reflected and a yellow light being reflected, and those will mix to make green. And if you mix red and blue, you get violet. And when you mix all of them together, you get black, because when you mix all of the colors together, none of the light will reflect. All of the light will absorb. So if I have a black shirt here, and I have my white light coming in, which is made up of red and green and blue and yellow and purple, and all of my rainbow colors, none of them will reflect. And if we get no reflection, that is an absence of a color of light. So all we see is black, because we have no reflection of that light back to our eyes. Now, light is what we call additive. It is not subtractive. It doesn't absorb things and put out only one thing. So pigments are subtractive because they absorb everything but the one color that they are. Light is additive because it is the color that comes to our eyes. There is nothing being absorbed there. And that's why they mix differently. Now, beyond having different colors of light, light has some pretty cool properties. So we talked about it being a transverse wave, meaning that as the wave moves this way, the particles move this way. So it looks something like this. And that's important, especially for something that we call polarization. You've probably all heard this when going sunglasses shopping before. So light is polarized when the electric fields oscillate in a single plane. And what that means is your wave only moves in one direction. It's in one plane. And a plane means two dimensions, like a sheet of paper. So in A, the light is polarized in this plane, up and down. In B, the light is polarized in this plane, which is side to side. But if we were to have two of these waves acting together at the same point, so we had some up and down and some side to side, that would not be polarized because that would be moving in two planes. It would be moving up and down and side to side. when you polarize light, you force it to vibrate in one plane. So it's like if you held a rope through the slats in a fence. If I was on one side of a fence and someone was on the other side and we had a rope through the fence, we would be able to make a standing wave in that rope, but only if we jiggled the rope up and down, like this. If we jiggled the rope side to side, we couldn't get a standing wave in there because the wave would continually hit the sides of the fence. It would not transmit through. So this is what's happening in polarized sunglasses. You are taking all of the light that is in the right plane and letting it through your sunglasses. And all of the other light that is not in the right plane gets stopped at your lenses and it can't pass through. So when we have light reflecting on something into our eyes, it is coming from every direction possible, right? If we have the road here, and light is reflecting off it. I'm going to use red, but let's pretend this is white light. It's coming in this direction, it's coming in this direction, it's coming in this direction. It might be vibrating side to side instead of up and down. It is all over the place. And because of that, we get something called glare. And glare is when you get all of these different orientations of light coming at different angles into your eyes. And it's kind of hard to look at. So polarized sunglasses eliminate glare by filtering out the parts of the light that aren't coming in the correct plane. So you can pretend that this cross right here is light in every direction. It's coming up and down, side to side, a little bit sideways or diagonal. And as it comes in, your polarized sunglasses have little imaginary slats in them that are up and down like this. So if they're up and down like this, only the up and down light will be able to pass through. The side to side light will not be able to pass through. So we're left with up and down. Now, if we take this same polarizing filter and turn it 90 degrees, we get a side to side filter. And this will only let through light that is side to side. Now, we already took out the side-to-side light. All we have left is up and down light. So, if we pass that up and down light through this filter, we block all of the light out. This is what would happen if you put on two pairs of polarized sunglasses and you had one turned at 90 degrees. You wouldn't get any light through those. They would be totally useless. But if you only take out one orientation of light, say you only take out the side-to-side light, that makes it a lot easier to see because glare is totally gone at that point. So your homework for tonight is to answer these three questions. Number one is, what is light? Tell me what kind of wave it is, and what it does, and how it travels, and what its speed is. Number two, how do polarized sunglasses work to reduce glare, which we just talked about. And number three, which has more energy, blue light or red light?